Dear student, in this video lecture, we are going to discuss about displacement current. It is part of electromagnetism, unit 6th, engineering physics, and I am Pankaj Jain, assistant professor in physics, Engineering College, Bikaner. Let us move on topic. Displacement current. All we know that according to Faraday's law of electromagnetic induction, when there uh, magnetic field or magnetic flux changes, when there is change in magnetic field or magnetic flux, it generates electric field or EMF. Therefore, a changing magnetic field generates electric field. Now a question arises, a question appears to us: whatever changing electric field can generate magnetic field. Okay, whatever changing electric field can generate magnetic field or not. And answer is yes. And this answer was given by Maxwell. Maxwell say that if there is change in electric field, electric flux in a bounded region, then it generates magnetic field. And it is very similar to the concept that when there is change in magnetic field, electric field generates. Okay, let us consider an experiment to understand displacement current. Uh, Two metallic plates are connected with a battery and a key. When key is done on, then when key will done on, here you can see that when this key is done on, then the parallel plate capacitor having metallic plates P1 and P2 will get charged. Okay, and during charging of capacitor, all we know that there will be flow of conduction current in wires. Okay, there will be flow of conduction current in wires during the charging of capacitor. Now we have taken two closed curve. One is named as C1, second is named as C2, and one is to uh, left hand side of plate P1 and other is to right hand side of plate P1. Okay, now for curve C1, Ampere's law may be written as integration for closed curve C1 B dot dl is equivalent to mu naught I, where I is what it is current flowing in conducting wires. Okay, and for curve C2, closed curve C2, we should write integration along closed curve C2 B dot dl is equivalent to 0. Okay, why it is equivalent to 0? Because no current flow in between plate P1 and P2 as we know. Okay, now if plate if curve C1 and C2 are taken very close to plate P1, then equation 1 and 2 cannot be valid simultaneously, because in left hand side we have same quantity uh, integration of b dot dl along closed curve C1 or C2, and in right hand side we will have two different quantities. Therefore these two equations cannot be correct, cannot be valid simultaneously if curve C1 and curve C2 are very close to plate P1, infinitesimal close to plate P1. Therefore a correction is required in these equations, equation number 1 and equation number 2, and this correction was given by Maxwell. Let us move on next page. Therefore, a correction is required in Ampere's law. This correction was given by Maxwell. He wrote Ampere's law as integration along closed curve for B dot dl should equivalent to, according to uh, Maxwell, it should be equivalent to mu naught multiplied by IC plus ID, where IC is conduction current, which flows in the wires, and ID is the displacement current. And concept of displacement current was introduced by Maxwell. ID is displacement current, okay, which generates displacement current generates due to change in electric field. Displacement current generates due to change in electric field. During the charging of plates, electric field will increase continuously in between plates of capacitor. Let us move on next page. Let us see this diagram again. Okay, when there will be charging of capacitor, current will flow in outer circuit as shown in diagram, and capacitor will be charged. There will be positive charge on plate P1 and there will be negative charge on plate P2, and these charges will increase with time during the charging of capacitor. Therefore, electric field lines, these are electric field lines. Therefore, electric field lines will increase with time during the charging of capacitor. Therefore, electric field in this bounded region in between plate P1 and P2 will change or will increase. Therefore, this changing electric field will generate a current which is named as displacement current. Okay, let us read here. Uh, the charging electric the changing electric field give rise to current known as displacement current. Okay, therefore, uh, if there is change in electric field in a bounded region, it generates a current, and this current is known as displacement current. Now, let us consider instantaneous charge on the plates of capacitor is Q. Q is the charge at an instant of time on any one of plate. Okay. Then using the basic definition for displacement current, ID is equivalent to dq upon dt. Here Q is replaced by CV, Q equivalent to CV for a capacitor, and again C is replaced by epsilon naught A upon D, which is capacitance of parallel plate capacitor, and V potential difference is replaced by E dot D, where E is electric field in between plates of capacitors, and D is the distance between plates of capacitor. Okay, with these replacement, D will be cancelled with D. Epsilon naught is taken outside. And what we get? E dot A. And E dot A is nothing but it is electric flux. E dot A is what? It is electric flux phi E. Okay, and epsilon naught is taken outside. Therefore, we have a formula for displacement current. ID is equivalent to epsilon naught d upon dt of phi E, where phi is what? It is uh, electric flux. Phi E is what? It is electric flux. This is formula for displacement current. Okay. Again, if we go through this formula, and and A is taken in the denominator of ID, then what we get? ID upon A. Okay, and here D is cancelled by D, and epsilon naught into E can be written as D. Epsilon naught into E can be written as D. D is what? It is electric displacement vector. Therefore, what we get? ID upon A. ID upon A is equivalent to D upon dt. Uh, Here ID upon A is displacement current density. ID upon A is displacement current density. Let us move on next page. ID upon A is what? It is displacement current density, which is represented by ZD. Therefore, ZD is equivalent to D, capital D upon dt. Or again we can write epsilon naught dE upon dt. These are formulas for electric displacement current density. These are formulas for displacement current density. Let us summarize our lecture. Hence, according to Maxwell, changing electric field in a bounded region give rise to current, which is known as displacement current. Okay, changing electric field give rise to a current which is known as displacement current. The effect of displacement current are very similar to that of conduction current. There is no change, there is no difference between effects of displacement current and conduction current. Okay, and it give rise to the magnetic field also. We all know that conduction current in wire give rise to magnetic field. Similarly, displacement current also give rise to magnetic field. Okay, therefore changing electric field which generates displacement current give rise to magnetic field. Okay, thank you students.